morning. Now next we discuss other transformations, that is the shearing and deflections. Okay, so last class we discussed the what is the transformations and what is the scaling. Okay, so now we discuss transformations of shearing and deflections. Okay, see shearing, that is it will be changing the object of the size. Okay, see here, y coordinates are unaffected but x coordinates are translated linearly with y, that is y dash equal to y and x dash equal to x plus y into h, that is xy1 equal to 1 h0 0 1 0 0 0 1 into xy1. See here, it will be changed the options, that is the normal objective position is here, but it will be changed the position like that. Okay, so that is the y coordinates are not unaffected, but x coordinates are translated linearly. Y is y, that is y dash equal to y and x dash equal to x plus y into h. Okay, see, intersecting of that points, you can define the objects as xy1 equal to 1 0 0 g1 0 0 0 1 into xy1. Okay, so shearing will not change the area of the particular objects. Okay, see, these are reflections. See, the based upon the x-axis, xy1 equal to 1 0 0 0 minus 1 0 0 0 1, that is xy1. In the y-axis, that is minus 1 0 0 0 1 0 0 0 1 into xy1, that is the it is the positive, that is the negative value. Okay, but here, so the positive x value and is the negative of x. In that way, 1 0 0 0 minus 1 0 0 0 1, when go for the y-axis, minus 1 0 0 0 1 0 0 0 1. Okay, so what's the transformation matrix? So likewise, we can transformation of the matrix, that is xy1 equal to complete opposites, that is minus 1 0 0 0 minus 1 0 0 0 1 into xy1. So reflection about y equal to x and reflection about y equal to minus y. Then rotate the, that is the standards of the particular matrix is used to rotate about the origin 0 comma 0. It is cos theta minus sin theta 0, sin theta cos theta 0 0 0 1. See, likewise we have to rotate the particular objects. See clearly, this is the rotation of the particular objects. So if you want to rotate about an arbitrary centers also, see, the rotate about an arbitrary point of p of px comma py by theta, and it will be changed like that. Okay, so to rotate about an arbitrary point p of px comma py by theta, to translate the object so that p will be coincide with the origin t of minus px comma minus py, that is px comma py, like that. So it will be change the objects. See here, and also rotate the object in order of theta. Translate the object back t of px comma py, likewise it will be translate the objects of the particular objects. So next, arbitrary rotation center, translate the object so that p will be coincide with the origin t of minus px comma minus py. Rotate the object equal to r of theta. So translate the object back equal to t of px comma py, put in matrix form, that equal t of px comma py r of theta, t of minus px comma minus py into p. So x dash y dash 1 equal to 1 0 px 0 1 py 0 0 1 of cos theta minus sin theta 0 sin theta cos theta 0 0 0 1 into 1 0 minus px 0 1 minus py 0 0 1, then x comma y comma 1. See, the standard scaling matrix will only anchor at 0 comma 0. What is an anchor? That is the instead of that is the starting and ending position are called as the anchors. Okay, so starting positions are 0 0, it's called as the anchors. Okay, now they take sx 0 0 0, sy 0 0 0 1, that is the object may be like displayed. Scaling means you can increase the same object. Here see, the object will be increased. So this is the smaller object, now it will be increase the size of an object. Okay, so if I want to scale about an arbitrary pivot point, to scale about an arbitrary fixed point px comma py, and translate the object so that p will be coincide with the origin t of minus px comma minus py. Scale the object as that is sx comma sy, it will be increased. Translate the object back t of x, is a translation. So scaling translations. Okay, based upon the pivot element. Okay, next we have discussed the next one. Next one is the polygon definition. So polygon is a figure having many slides. It may be represented as a number of line segments end to end to form up a closure figure. So the line segment which form a boundary of polygon are called as the edges or slides of the polygon. So the end of the sides are called as a polygon vertices. See, triangle is the most simplest form of polygon, having three sides and three vertices. So what are the types of polygons? Mainly there are three types. There is the convex and concave and complex. So convex polygon is a polygon in which if we take any point which are surely inside the polygon, and if we draw a joining these 2 points, and if all the points on that line slice into the polygon, then such a polygon is called convex polygon. So concave polygon is a polygon in which if we take any 2 points which are surely inside the polygon, and if we draw a line joining these 2 points, and if all points on that line are not lying inside of the polygons, then can called as the concave polygons. Next, in the computer graphics, a polygon which is neither convex or non-concave as a complex polygon. So the complex polygon includes any polygon which intersect its of the polygons of the overlap itself. The complex bond is the boundary. See, likewise we can represent the polygons. Okay, xy 55759371513355. Okay. See next. So usually surface object, usually polygon. See why the polygons is boundaries equal to linear equations that fill the algorithms can approximate most curved surfaces with polygons. Shading is easier. Okay. So approximating a curved surface with polygons, more polygons, better detail, but more vertices polygons to process, also called fitting and surface with the polygon meshes. So polygon is a figure with three or more vertices connected in a sequence by straight line segments. So this is the three vertices polygon. This is the four vertices. This is the standard and simple polygon. These are the cross edges. So in computer graphics, polygon not always in the same plane. Round off error. There is after transformations. Fitting the surface makes non-planar polygons. There is a quadratic half of the. Then uses triangle single plane per triangle. So degenerate the polygons. There is often used to describe polygon with three or more collinear vertices. It generates a line segment. For example, in extreme case, triangle with no area. Okay, so here the triangle we have defined the three vertices of v1, v2, v3. But here taken v1 v2 is one position, v3 and v4, that the edge between v1 and v2 has the length is 0. If there is no length between the v1 and v2, in that way we can degenerate the particular polygons. So convex and concave, the interior angle is inside of the polygon boundary formed by two adjacent edges. Convex, all interior angles less than 180 degrees. Concave equal to one or more interior angles greater than or equal to 180 degrees. So by looking at vertices compared to edges lines, convex for all edges lines, all other vertices are no one side. Concave for one or more edges lines, some of the vertices on one side and some are on the other side. So also one or more edges lines will be intersect the other edges. So this is the example. Likewise, this is the convex, this is the concave, so this is also convex, this is also concave. Okay, some edges, some vertices are on the inside of the, some other are the outside. Okay, so the convex is the degree of the angle is below, less than of 180 degrees. In the concave angle is it may be greater than or equal to 180 degrees. Okay, in that way we can define this, which is the convex, which is the concave. So less than 180 degrees it is concave, the angle of angle is, and angle is greater than 180 degrees it is called as the concaves. Okay, this is the concave. So OpenGL cannot deal with the degenerate polygons or concave polygons. So programs must detect and pre-process the particular objects. So directly we cannot degenerate when the programs are using of that one. It will be changing the positions or pre-process to the particular polygons. So degenerate polygons are detect and remove. Concave polygons detect and split into the convex polygons. So whenever we can take the concave polygons, we can split into the convex because of the concaves are very difficult. In that way we can form into the different type of the convex problems. So because of when we take the concave, we can convert into the convex polygons. Next, a vector is equal to n by n or 1 by n matrix. In computer graphics, n is usually 2 comma 3 comma 4, that is a homogeneous coordinates. Components of the vector 2D, that is x and y values. Okay, 3D is x, y, z, and 4D is x, y, z, and w. So vector interpret has location w equal to 1, direction w equal to 0. So scalar equal to single value or 1 by 1 vector, v equal to x, y, v equal to x, y, z, v equal to x, y, z, w. That is two-dimensional, three-dimensional, and four-dimensional. See, in three-dimensional, this is the point of x, y, z. There is x, y, z. This is the 3D direction. So how the direct to the, likewise, this is the 3D directions. So x comma y comma z. Okay, see, length of the vector and the zero vectors, we can use Euclidean distance for the length. So because of all the convex and concave, we can implement using of the mathematical applications. So here one of the mathematical application is Euclidean. So already we have learned the Euclidean formulas in the m1 or m2. So okay, now they use Euclidean distance for the length v equal, there is a model v equal to root of x square plus y square plus z square. A vector with a length of 0 is called the zero vector. That is v equal to 0 0, v equal to 0 0, and v equal to 0 0 0 0. Okay, so scaling vector, so scalar times a vector equal to scalar times the component of the vector. Example, multiply 5 by a 3D vector a, 5 by a equal to 5 into xa ya za equal to 5 into xa, 5 into ya, 5 into za. Okay, based upon that we can define the scaling vectors. See, normalized vectors. So normalized vector equal to divide vector by its length v to makes length equal to 1. So equivalent to multiplying vector by 1 or by modulus v. Resulting vector is called normalized vector. Okay, so whenever we have to perform the different type of the operations, then we can perform the normalized vector. So this is not the same as normal vector, although normal vector are often the normalized. That is, see, for equation v by moduli v equal to v by root x square plus y square plus z. So there is an Euclidean equation. Now x by root x square plus y square plus z square, y by root x square plus y square plus z square, z by root x square plus y square plus z square. Okay, so whenever we can draw the polygons, these are the most important to using of the normalized vectors. It may be based upon the 2D or 3D or 4D. If it's 2D, we can take x comma y. If it's 3D, we can take x, y, z. If it's 4D, x, y, z, w. So mainly we are using 2D and 3D. See, add and subtract vectors. Can component says a plus b is equal to xa plus ya plus za plus xb yb zb equal to xa plus xb ya plus yb za z plus b. If we subtract a minus b, that equal to xa ya za minus xb yb zb equal to xa minus xb ya minus yb za minus zb. Okay, so geometric interpretations adding to, that is the putting head of one vector on tail of the other. Subtracting is gives directions from one endpoint to the other. So likewise, these are the examples. See here, this is an addition, this is in subtraction. Check it once. So adding is the putting head of one vector on tail of the other. Subtracting gives the directions from one endpoint to another endpoints. So whenever we take the different type of the endpoints, both of the endpoints we can from one to another we can link up. There is a minus b, and it will be head on the one vector, tail on the others. So dot product is a dot b equal to xa xb plus ya yb plus za zb. So result is a single number, that is scalar, and the name of the name for the dot product is the scalar product. So dot product of vector with itself equal to square of length of vector, that is a dot a equal to x square plus y square plus z square equal to a square, equivalent to a into b equal to a b cos theta. So where theta equal to smallest angle between the two vectors. If the vectors are normalized, then a equal to 1, b equal to 1, a dot b equal to cos theta. So this is the example. Okay, so product is a into b, that is a dot b, that is a product xa xb plus ya yb plus za z plus zb. When take a square, that is a dot a, x square plus y square plus z square. Okay, based upon that, model a equal to 1, model b equal to 1, ab equal to cos theta. So likewise we have to draw the angles. Look at sign of the dot product, check angle, that is a dot b greater than 0, that is vector points is similar in direction, 0 less than equal to theta less than 90 degrees. A dot b equal to 0, vectors are orthogonal, that is perpendicular to each other, theta equal to 90 degrees. Less than 0, vectors pointing away from each other, 90 degrees less than theta less than equal to 180 degrees. So for normalized vectors, dot product ranges from -1 comma 1, a dot b equal to 1, vector pointing in the exact same direction, theta equal to 0 degrees, a dot b equal to 0 to vectors are orthogonal, that is perpendicular to each other, theta equal to 90 degrees, a dot b equal to -1, vectors pointing in the exact opposite directions, theta equal to 180 degrees. Okay, see, a dot b equal to ab cos theta, cos 0 equal to 1, cos 90 equal to 0, cos 180 equal to -1. Okay, so this is the different type of the angles. Based upon the angles we can define, so which the particular area, which direction will be there, that is greater than 0, the similar directions, equal to 0 orthogonal, less than 0 it may be greater than or equal to 180 degrees. For Norman vector, based upon the -1 comma 1, that equal to 1, theta equal to 0, a dot b, the vectors are orthogonal, that is perpendicular to each other, theta equal to 90 degrees, a dot b equal to -1, the vectors are pointing in the exact opposite direction, theta equal to 180 degrees. Okay, so likewise we have defined the different of checking the different of the angles of the particular dot products. In the cross product, w equal to wx wy wz equal to u into v equal to uy vz minus uz vy, uz vx minus ux vz, ux vy minus uy vz. So it is also called as a vector product, that is the result is a vector formations. So given two vectors u and v gives vector w that is orthogonal to both u and v. U and v and w from right-handed systems, that is can use right-handed rule of on u and v in that order to get w. Example x6 y z axis. The length of w equal to u into v is equivalent to w equal to e into v equal to u v sine theta. Okay, This is the cross product. So where again theta equal to smallest angle between u and v. If u and v are parallel, that is theta equal to 0 degrees to sine theta equal to 0 to get the 0 vector for w. So likewise we have defined the cross product. This is the dot product and cross product. In cross product, uv equal to uy vz minus uz vy, uz vx minus ux vz, ux vy minus uy vz. Okay, that is equal to uv sine theta. Okay. See, cross product of order matter, that is order the cross of the product u cross v equal to minus v into minus v cross u. So property is simply you can say anti-commutativity. Okay, that is the where is the right-handed rules. So computing the cross product arrow scheme, that is the follow diagonal arrows for each arrow, multiply elements along arrow times sign at top. The ex equal to x-axis, ey equal to y-axis, ez equal to z-axis. Okay. So ex, ey, ez, that is the minus of ex, ey, ez, ux, uy, uz, vx, vy, vz, and ux, uy, that is the u cross v equal to plus ex, uy, uz plus ey, uz, vx plus uz, ux, uy minus ex of uz, vy minus ey, ux, vz minus ez of uy, vx. So based upon that different type of these schemes we have performed. There is a sort of scheme based upon that we can compute the cross product of the particular given the x and y axis. So ex here x and y z is taken as the ex equal to x axis, ey equal to y axis, and ez equal to z axis. And detecting and splitting the concave polygons, there are two ways we can do this: vector method and rotational method. In the vector method, check interior angle using cross product, and rotational method, rotate each edge in line with the x-axis, that is check if vertex below x-axis. So based upon that we can define the detect and split in the concave polygon. There are two ways we can do this: vector method and rotational method. So vector method, check interior angles using the cross product. In rotational method, rotate each edge in line with the x-axis to check if vertex below the x-axis. So splitting with vector method, that is ek equal to vk plus 1 minus vk, that is transform to xy plane if it is necessary. You can transform the xy. Get edge vectors in the counterclockwise order, that is ek equal to vk plus 1 minus vk. For each pair of consecutive edges vectors, get cross product. In concave, negative z component to split polygons along first vector in cross product pair have to intersect this line with other edges. Repeat process with two new polygons. Okay, see for example, e1 cross e2 greater than 0, e2 cross e3 greater than 0, e3 e4 less than 0, e4 e5 greater than 0, e5 cross e1 is greater than 0. So based upon that we have defined the different type of the vector methods. So based upon that we can draw the diagram. See, this is the operation of the vector method. e1 e2 e2 e3 e3 e4 e4 e5 e5 e1. Okay, so splitting by rotational method, transform to xy plane if necessary. For each vertex vk, move polygon so that vk is at the origin, rotate polygon so that vk plus 1 is on the x-axis. If vk plus 2 is below x-axis, polygon is concave, split polygon along x-axis. Repeat concave test for each of the two new polygons. So stop when we have checked all the vertices. Likewise we have to perform the each rotational method. See, this is an example. Okay, splitting the convex problem. So every three consecutive vertices to mark the triangle. So different from the polygons there, but here we can define the different from the points. In each and every point we can define three take points, take the consecutive vertices and make the triangles. So remove the middle vertex and keep going to the three vertices. So plane equation, need plane equation, collision detection, ray tracing, ray casting, etc. Need normal of polygons, writing shadings. That is ax plus by plus cz plus d equal to 0 on the plane, ax plus by plus cz equal to 0. Behind the plane, ax plus by plus cz plus d less than 0. In front of the plane, ax plus by plus cz plus d greater than 0. So calculating that A 1 y1 z1 1 y2 z2 1 y3 z3 B x1 y1 z1 x2 1 z2 x3 1 z3 C x1 y1 1 x2 y2 1 x3 y3 1 D x1 y1 z1. So based upon that, we have to define the different type of the equations A B C D. A equal to y1 of z2 minus z3 plus y2 of z3 minus z1, y3 of z1 minus z2. B equal to z1 of x2 minus x3, z2 x3 minus x1, z3 x1 minus x2. C equal to x1 of y2 minus y3 plus x2 of y3 minus y1 plus x3 of y1 minus y2. D equal to minus x1 of y2 z3 minus y3 z2 minus x2 of y3 z1 minus y1 z3 minus x3 of y1 z2 minus y2 z1. Okay. So this is m equal to 1 2 3, that is 1 into 4 minus 2 into 3. M equal to 1 2 3 4 5 6, that is I of 2 into 6 minus 3 into 5 plus J of 3 into 4 minus 1 into 6 plus K of. Okay. Likewise, we have to perform the operations of the polygons. And also 3D dimension also we have to take the 3 dimensions x, y, z. But here you can take in 2 dimensional can take x comma y. In 3 dimensional we can take x, y, z. Okay. Thank you.